We were wrong about 3I to ATLS, not a little wrong, deeply wrong. For decades, scientists like me have trusted models and rules. We use those rules to call this thing a comet. That choice guided every step we took. It shaped how we measured, how we predicted, and how we prepared. But that label, comet, now looks wrong. And that mistake cost us understanding. When 3AIvoice first arrived in our sky, a fuzzy glow, a small cloud of gas, a path that pointed back out of the solar system. It fit the shape of a comet. So we treated it like one. We watched, we measured, we wrote papers. The world watched with us. Then the data started to disagree. We saw motion that did not match a normal body. It slowed in ways no comet should. Comets get pushed by sunlight and by gas jets. They usually speed up near the sun. This one slowed. Little by little, then more. It moved as if something were braking it. Not random drift, not wobble, but a steady, controlled reduction in speed. We tried to explain that with normal ideas, maybe odd jets of gas, maybe sunlight bouncing strangely, maybe measurement error. We looked for anything that would let us keep calling it a comet, but every correction broke the next assumption. The more we forced it into the comet box, the more the data refused to fit. Then we got images from orbiters near Mars. These pictures showed shapes on its surface that made no geological sense. Hexagons, regular holes, bright rims, arranged patterns like parts of a machine. We tested every natural process we know. Thermal cracks, mineral shakes, crystal growth. None fit cleanly. The simplest reading was the scariest. The shapes looked made, not grown. Next came the chemistry. The gas around it had almost no water. Instead, the spectrum was heavy in carbon dioxide and strange molecules we rarely see in comets. Water is the rule for icy objects from cold regions. Finding almost no water is like seeing a fish that breathes fire. It is possible, but it is not normal. As the object neared perihelion, its closest pass to the sun, we expected the usual show. Heat rises, ice turns to gas. Comets flare and shed pieces. Scientists hope for a bright tail, a cloud of dust, or pieces that telescopes could catch. We prepared every instrument on Earth and in space. We trained every eye we had. What we saw instead was the opposite. During perihelion, instead of venting more gas and brightening, the object's gas output fell. The cloud shrank. Temperatures on its surface rose to hundreds of degrees. By every basic rule, it should have exploded into a million fragments. But it did not. It swallowed the heat. It did not radiate the energy we expected. It looked like something engineered to hold heat inside. We modeled heat flow in many ways. We tried rock, metal, porous ice, composite shells. None of the models could hide that much energy. To store that heat without blowing apart required structures that move heat, trap it, or convert it into other forms. That is engineering, not geology. Then the big impossible thing happened. The object did not just slow. It performed a huge change in speed at precisely the right time, while deep in the sun's gravity well. The numbers are brutal. The change required force far larger than any natural cometary process could produce. We calculated again and again. The only way to match the data was to assume a continuous directional thrust for many hours. Not jets of gas from random vents. A steady, controlled push. That is not a comet doing natural chemistry. That is propulsion. Even worse, the timing aligned with the Oberth effect. That is a trick rocket scientists use do a burn while moving fastest near a massive body and get the biggest payoff. If you want to change your path with little fuel, you do it near the sun. The object used the sun's gravity like a machine uses a lever. It applied force when it mattered most. The result, instead of flying out of our system, it moved into an orbit that keeps it near the inner planets. It did not pass through, it stayed. Think about that. An object arrives from interstellar space, aims precisely into our plane, survives a brutal passage close to the sun, stores energy like a battery, and fires at the perfect moment to change its path. That change keeps it in our neighborhood. The conclusion is unavoidable. This thing acted with purpose. So we have to ask a new set of questions. Who or what can make such a thing? Why aim at our system? Why choose to remain? We can imagine three big options. First, it is technology. A probe built by an intelligence elsewhere. Second, it is a form of life, something that evolved in interstellar space in ways we cannot imagine. Third, it is something that mixes categories. Not life by our standard shapes, not a machine like we build, but a new kind of organized system that operates under physical rules we do not yet understand. Each option breaks our categories. If it is technology, then a species launched this probe a very long time ago. It survived a long trip, maintained systems, and knew enough to aim near the sun and use its gravity. That implies knowledge of orbital motion beyond guesswork. It could mean they either predicted us, or many such probes aim at many star-like suns. If they predicted us 2 million years ago, how could they know we would become detectable? If they launched probes at many sun-like stars, our system was just one of many targets. Either idea is huge. If it is life that evolved between stars, then life can arise in extreme cold and thin gas. It would show that life is more flexible than we thought. It would mean chemistry in deep space is capable of building systems to capture energy, move, and make decisions. We would have to rethink how life begins. If it is a new category entirely, then the universe has modes of organization we never imagined. That would push physics and biology into a new realm. Our vocabulary would be too small. We would need new ways to classify and test. For now, we simply do not know. But we cannot use old labels anymore. Calling it a comet hides more than it shows. That name gave us comfort and direction. But comfort is not the same as truth. So in these early hours after perihelion, the scientific community must change strategy. We must stop assuming naturalness. We must treat the object as an active phenomenon. We must gather every form of data we can: thermal maps, radio listening, optical imaging, magnetics, and particle counts. And we must prepare for the possibility it might respond to our actions. This is not a call to panic. It is a call to clarity. We were wrong to assume. We were wrong to force the data into familiar boxes. Now we must listen with new ears. What happened to thyroid ALS forced that change. It showed us that our models are tools, not rules carved into stone. When the tool fails, we must pick another tool. That is the heart of science. In the next part, we will look at what the world did after it vanished. We will examine the signal that was later recorded and the debate about how to reply. We will walk the thin line between curiosity and caution. We will ask what it means to face intelligence or unknown organization in our space. But first, understand this. A single object changed how we think about our place in the sky. It told us our assumptions could be wrong. And it told us that the universe may be deliberately more interesting than we ever allowed ourselves to believe. The days after perihelion were filled with silence and noise at the same time. Silence from the object, noise from our machines and our talk. Telescopes looked, radios listened, labs ran models, governments held meetings, newsfeeds filled with opinion and fear. Scientists, though, focused on data. At first, agencies published short statements. Tracking paused during solar conjunction, they said. That was true. The sun blocks view in a way that makes astronomy blind for a time. But when observations resumed, the object was not where our predictions said it would be. Not only did we fail to see it clearly, but our searches found no dust, no fragments, no extended tail, nothing to show it had died or broken apart. Then the radio teams found something new, a narrow signal at the hydrogen line frequency. That frequency is special. Hydrogen is the most common element in the universe, and the 1.42 GHz line is a reference frequency many SETI researchers believe other intelligences could use. The signal repeated in a regular pattern. It carried structure. It looked like a message. At first, people argue if the signal was real. Many telescopes recorded it. Independent groups checked the data. The pattern repeated every 47 seconds. The signal was not broadband noise from the sun. It was coherent. It had layers of encoding. Some parts looked like basic math prime numbers, simple ratios. Those are the kind of things you use if you want to establish a bridge of understanding with an unknown listener. The signal was not broadcast in all directions. It was aimed. The beam pointed to Earth. That fact changed everything. This was not a passive beacon. It knew where we were and chose to send the beam at us. It recognized Earth as a place to target. That does not mean it is friendly. It does not mean it is hostile. But it does show intention. In the halls where policy is made, the conversation moved fast. Some urged immediate reply. Answer back with a greeting made of math. Show we understand basic concepts and ask questions. Others urged silence. The worry if it can send a beam directly at us, it can also receive and learn. Any reply could reveal our location, our power, our knowledge. If the sender is dangerous, we might hand them the map. There was a third idea, observe only. Record everything. Try to decode before speaking. But decoding takes time. Every hour we wait could mean they move, leave, or choose to interpret our silence in ways we cannot predict. In labs, teams work nights. They unwrapped the signal like a present wrapped in many layers. The base layer seemed to teach numbers. Then came geometry. Then came patterns that looked like representations of simple physical constants. The coding style matched how we would try to teach an outsider. Start small, build up to complex. Some mathematicians argued the patterns included images when reconstructed with the proper frame. Others said that claim was premature. The risk of pattern seeking is high. Our minds love to find faces and shapes and noise. So groups used blind tests. They let software search for consistent frames without human bias. Several times, images with simple geometric content surfaces circles, a ratio, maybe an axis. Nothing clear like a picture of a ship or a planet, but the structure was undeniable. Meanwhile, dynamic models showed the object's new orbit could keep it near Earth for months. If it stays in the inner system, we will have many chances to study it. If it leaves, we might lose contact forever. The choice of staying close could be intentional. The object wanted time to interact. Different scientific camps formed. One camp said, "This is a probe meant to observe developing worlds." Senders placed it near the orbital plane of the system to observe planets where life is likely. They sent many probes to many suns. The math of probability supports this idea if probes are common. Another camp said, maybe it was launched with a selection algorithm. Senders predicted which systems would develop life and timed launch accordingly. That possibility implies knowledge of planetary evolution beyond current science. Others proposed it is not sent by a civilization at all, but is emergent complexity. There are processes which, over eons, could create systems that process information and act on it. Hard to imagine, yes. But in the face of persistent anomalies, we must include the impossible as a candidate. Policy teams added a new layer of worry. Some nations wanted to keep information controlled until they understood more. They feared panic or exploitation. Others pushed for open publication so global scientists could help decode. The result was messy public statements and leaked memos. That fueled online theories. Some claimed cover-ups. Others claimed we had proof of aliens. Reality sat in the middle: raw data, quiet labs, and small steps forward in decoding. The story of 3I also deepened in human meaning. If the object is intelligent, it means someone out there took notice of our world. If it is merely a probe, someone out there is curious about life. Either idea changes our sense of place. We also faced ethical questions. Who speaks for humanity? If we are to reply, which message should represent all of us? Scientists argued for a measured, inclusive message using universal math and careful phrasing. Politicians feared missteps and the possible political fallout. Religious leaders looked for guidance. Historians and philosophers asked what consent from a global public should look like. These debates will not resolve in a single meeting. For now, the safest path is transparency in science. Publish the data. Let the world see the patterns. Open eyes make better decisions than closed ones. But transparency has limits when it touches national security. The balancing act is hard. In the labs, engineers simulated possible replies. A simple return of prime numbers and fundamental constants seemed safe. It signals understanding, but reveals little about our technology or vulnerabilities. Yet even that small signal is information. It confirms we exist openly, which we already do via radio leakage, but this would be a targeted reply. Meanwhile, measurements continued. If the object is indeed listening, it may change its behavior based on our transmissions. That possibility means we must think carefully about timing and content. We must consider consequences of being noticed by something that knows orbital mechanics well enough to stay near our planet. So far, the object has not shown overt hostility. It did not fire anything at us. It did not attempt to alter Earth's orbit or environment. It changed its path to stay close, and it broadcast a signal that teaches math. Those are not aggressive acts. They are acts consistent with observation and communication. But caution is wise. We do not know why it chose to make contact now. There are many possible reasons: curiosity, study, a search program, or a longer-term plan we cannot grasp. The safest immediate course is to gather data, consult widely, and coordinate globally before any reply that might reveal more than we intend. In the next part, we will explore how society responded, the politics, the fear, the hopes, and the quiet work behind the scenes. We will look at the conversations among leaders, the planning for potential missions, and the questions ordinary people asked when told the truth. This event will change our civilization in ways both small and great. We are living at the edge of that change. People notice things first through headlines, then they read the papers, then they argued. The arrival of AIvoice and its strange behavior forced a new kind of public conversation. It was not just about rocks and space anymore. It was about identity, readiness, fear, and trust. On TV and in forums, many voices shouted. Some proclaimed doom. Others spoke of a golden age of contact. Between those extremes, the steady work of institutions continued. Universities, observatories, and independent scientists kept doing science. That work mattered most. One core question drove the debates. One is the risk if we respond. Risk comes in forms we can imagine: biological, informational, technological. If we were to share too much, we might help someone build tools that hurt us later. If we withhold and they are benevolent, we might lose an opportunity for knowledge and improvement. History gives no clear answer. Encounters on Earth between unequal societies often ended badly for the weaker side. That memory shapes many fears, yet our situation is also unlike those histories. This encounter might be purely observational. Many argue that advanced observers would avoid interference. The probe stayed hidden and careful for millions of years. Perhaps restraint is the rule among advanced civilizations. If so, their aims could be scientific, not predatory. But even a non-hostile probe brings profound social effects. The knowledge that we are not alone changes religions, politics, and science. It forces us to ask whether human law can apply to unknown intelligences. It forces debate about who speaks for humans and what rights we might want to assert. Could we demand information? Could we set terms? Or would any demand be meaningless against an intelligence that can arrive from light years away? Governments began emergency talks. They invited scientists, ethicists, and diplomats. They discussed possible responses: remain silent, send a controlled, simple message, or attempt to physically intercept the object with a probe. Interception posed technical challenges. The object was not stationary. It moved, stored energy, and appeared to maneuver. A rendezvous mission would take time to plan and build. In the meantime, sensors could be positioned to learn more. The idea of an interception split teams. Some argued it was essential. You cannot fully decode a machine from a distance. Close study could reveal materials, mechanisms, and intent. Others argued an interception risks provoking a reaction we cannot handle. What happens if the probe interprets our approach as a threat? Would it flee, or would it take steps to defend or hide? In labs, engineers sketched rapid mission plans. Use existing boosters and trajectory tricks, they said. Use gravity assists. Use small quick probes to test behavior at distance. Yet even an idea of a test mission would be publicly visible and politically sensitive. Cultural responses were immediate. Some groups found new meaning in the story. For some, it was confirmation of beliefs. For others, it was a crisis of faith. Education systems scrambled to include the data into classes. Media organizations released verified data sets for public use. The best scientists urged calm. They asked people to treat evidence with care and not to rush into dramatic conclusions. At the same time, social media exploded with speculation. Memes, videos, and conspiracy theories spread faster than careful analysis. That is human nature. We try to make sense of an event that breaks our prior map. The best counter to confusion is transparency and good communication. Teams that publish clean, simple explanations helped reduce panic and improve public understanding. In secret, intelligence and defense teams watched too. They tried to assess technical capabilities and intent from the signals and motion. They compared the pattern of the broadcast to known protocols. They monitored for any change after human transmissions. So far, the object listened more than it acted. That, again, suggests its priority is observation over intervention. Philosophers joined the conversation too. They asked, does contact change moral obligation? If another intelligence watches us, do we owe it anything? How should we frame messages that represent many cultures, languages, and values? The hope among many ethicists was to form a global approach, a measured, inclusive message created by many voices, not a single nation. Industry also reacted. Space companies explored whether their assets could be repurposed to help. Telescope time was bid for. Private missions proposed to send small probes quickly. The private sector can be nimble, but rapid action raises risks of miscommunication and mixed goals. Coordination matters. Children watched too. They asked their parents simple questions. Are we safe? Will they hurt us? Are they like us? Those questions drove home a truth. Beyond politics and science, the human heart had been moved. We are a species defined by curiosity and fear in equal measure. This event touched both. Back in the labs, decoding efforts made slow progress. The repeated patterns in the broadcast were not a full language. They were a bridge. The message makers used prime numbers and geometry to prove intelligence. The next layers might build images of motion or chemistry. Decoders worked through permutations. They tested whether the signals might hide audio or physical data. They considered whether modulation carried mathematical maps. Some teams thought they detected hints of a map, like structure showing a star pattern or orientation. But ambiguous results require care. False positives are easy. Many scientists argued for a simple first reply, basic mathematical truths, and a map showing our sun and planet positions. But any map reveals where we are. Do we want to expose our exact location? Perhaps the senders already know. Our radio leakage for a century means we are not perfectly hidden, but a precise, targeted map could help them home in. Therefore, a cautious approach gains support. Send minimal but clear signals that show we understand numbers and physics without exposing technology or cultural detail. Let that be the first step. Use a pattern that invites a response without giving away our entire playbook. Throughout all of this, the object remained the center. It sent no new threat. It did not accelerate toward Earth. It stayed within bounds that suggested observation, not attack. That gave many scientists hope and reduced the urgency for risky action. Finally, a global coordination committee formed. Scientists, diplomats, and ethicists from many nations met to draft guidelines. Their first rule prioritized data sharing. Second rule, consult internationally before any reply. Third rule, keep the public informed with verified information. It was not perfect, but it was a start. In the next part, we will look deeper into the science of decoding and what a carefully chosen reply might look like. We will also explore the long-term implications, how this event could change our technology, our law, and our sense of who we are. We stand at a pivot point. The arrival of Three Eyes AIvoice and its strange behavior forced us to choose how to act as a species. The easy answers, stay silent, fire rockets, hide, were all partial and risky. The wisest path seemed to be one of measured curiosity and collective responsibility. First, science must keep the lead. Open data, independent checks, and global cooperation are the strongest tools we have. When many eyes look at the same data, errors fall away. When many minds translate the same signal, the chance of misreading decreases. That is why a broad scientific coalition formed to decode, to verify, and to advise. Second, diplomacy must hold. No single country should decide alone. A message representing all of humanity must come from all of humanity. That is hard. It takes time. Yet this is the kind of problem we must manage together if we want legitimacy and the best chance of wise action. Third, caution is a virtue. We have nothing to gain from reckless acts. If the object can point a beam at us, it can point a beam at anything. Any action that reveals more than necessary